Okay, we're looking at chapter 6, which is further hypothesis tests. Now, I'm splitting this chapter up into two sections and kind of giving them different titles to help us remember the content a little bit better. So I'm going to go with chapter 6A, which is looking at the chi-squared distribution for the variance of a normal distribution. And then chapter 6b is a different distribution, which is called the F distribution, which is for the differences in variances. Now, they are linked as they are both concerned with the variance, but they are two distinct distributions that will overlap in some different exam questions. So the first half of the chapter, 6a, is going to be these two ones that we have here. And then the second half of the chapter, chapter 6b, are the 6c and 6d exercises. In the exam questions document, this chapter covers the following sections. So the green part is this chi-squared distribution stuff, which is to do with doing hypothesis testing on the variance of a normal. And then the F distribution is going to be the stuff that's associated with these yellow bits that we've got here. Now, there's going to be a pretty crazy proof coming up in this video that you can skip if you want to, but it's kind of fun to see what university level statistics might look like. So further stats 2, chapter 6a, we're looking at the chi-squared distribution, and really this is to do for variance that we have here. So let's just remind ourselves about what happens with the mean. If we take several samples of size n from a population x, we know that x bar is an unbiased estimator for the population mean mu, as long as n is big enough, and we know that the sample means are distributed normally. What I mean by this is we know that x bar has a normal distribution with a mean of mu and a standard deviation, a variance of sigma squared over n. So we know the distribution of the sample means. Now, we also know that s squared is an unbiased estimator for the population variance sigma squared. But unfortunately, its distribution is not that simple and is certainly not normally distributed. We cannot use the central limit theorem on the variance estimator because it doesn't have this normal distribution at all. Instead, and this is where you're going to be like, what? An adapted version of s squared, or an adapted version of the sample variance, has a chi-squared distribution. Yes, it's come back from Further Stats 1. If you haven't learned it from Further Stats 1, you better know it right now, because we need to know the chi-squared distribution. So really bizarrely, if you take the sample variance, you multiply it by n-1 and you divide it by the population variance, then that thing has a chi-squared distribution with n-1 degrees of freedom. Now, you can either take my word for this, or you can stick around for a university level proof. Now, I suggest you watch it and see how it works, but it's crazy. But I want to show you that it's there because I don't like these things. In the textbook, I think it says just something like, yeah, this is what it is. Let's get on with it. And I don't like things like that. It makes me feel a bit uneasy. It's going to rely on the fact that a chi-squared distribution is the sum of lots of standard normal distributions squared. Now, if you watched my introduction videos on the chi-squared distribution for Further Stats 1, you will remember this. I talked about that we were taking a normal distribution, a standardized normal distribution where the mean is 0 and the variance or standard deviation was 1, and we were squaring them and adding them up. So that if we had something like Q3, which was the chi-squared distribution with 3 degrees of freedom, it was taking 3 observations from a normal distribution and taking those 3 observations, squaring them, and adding them together. We could write it in this way if we wanted to, but we write it as chi-squared because it is simpler and we don't need to write out like a long list of different things. So it is relying on the fact that chi-squared distributions is literally the sum of normal distributions that are being squared, okay? So if you want to stick around, you can. If you want to skip this video and just go straight to doing some examples, you also can do that. So we're going to prove that n-1 times the sample variance over the population variance has a chi-squared distribution with n-1 degrees of freedom. So given that the sample variance is the sum of x minus x bar squared over n-1. We know that. That's like the original definition that we had of s squared of the sample variance. We're going to show that this thing has a chi-squared distribution. So we're going to start off by saying to ourselves, okay, we're going to do this for a normal distribution. We're going to say that X has a normal distribution with mean mu and variance sigma squared. We are doing this for a normal distribution here. And we're going to remind ourselves of the fact that Z has a normal distribution with a mean of 0 and a standard deviation or variance of 1 that we have there. Okay. We also talked about the fact that if we had Qn, that would be something like Z1 squared plus Z2 squared, all the way up to Zn squared. In other words, you're summing n different normals, n different squared normal distributions of the standard normal distribution together. We would say that Qn is distributed with a chi-squared distribution with n degrees of freedom. I'm kind of repeating what I've said here, but putting it in sort of the general kind of terms that we've got here. So this is what we're going to try and look at. Let's first of all investigate what is n minus 1 s squared over sigma squared. So I'm going to say that n minus 1 s squared over sigma squared, doing a bit of substitution here of this formula. I'll substitute that in there. It is going to be n minus 1 over sigma squared multiplied by s squared, which is the sum of x minus x bar squared over n minus 1. Now the n minus 1s are going to cancel, and so it is the sum of x minus x bar squared all over sigma squared. So this is the thing. If I can find this thing here, I'm going to be very happy. If I can find the distribution of this, then I'm happy. So I'm just going to jot this down. I want to find its distribution. If I can find that thing in yellow, if I can find that one's distribution, then I found the distribution of this thing, and I'm hoping that this thing is going to have a chi-squared distribution. Okay, let's now return to this sort of definition that we have over here. So we know that this is the sum of all of these normal things that we've got here. So I could say that Z1 squared, let's write this down, Z1 squared plus Z2 squared all the way up to Zn squared, that is going to have a chi-squared distribution with degree n that we have there. And I'm going to try and write this now using some sigma notation instead. So this is saying that the sum from r equals 1 to n of zr will have a chi-squared distribution like this. Now I know something about z, okay? I know that z, I can take the x part that we've got and I can standardize x so that I can replace it with z that we have here. Oh, sorry, this should say z squared. So let's replace it. I'm going to use the fact that z is equal to x minus the mean divided by the standard deviation. So the sum from r equals 1 to n of x minus mu over sigma all squared, that is going to have a chi-squared distribution. I'm never good at drawing the chi-squared bits with degree of n. So I'm going to now try and investigate this thing that we've got here, and I'm going to do this in purple on the next page. So the sum from r equals 1 to n of x minus mu over sigma all squared. Okay, well, I think what I can do in this case is try and split this up in a sneaky way. And this is the sneakiest part of the proof. I am going to rewrite this numerator so that it is identical. But I'm going to do a little trick. I'm going to change it so that the numerator is written as x minus x bar plus x bar minus mu. Now, we can all agree that these things are going to cancel out, so it actually hasn't changed the whole overall part of the numerator, okay? And that is the sneakiest thing that we're going to do in this proof, and that's all being divided by sigma squared. Now, I'm going to bracket this. I'm going to bracket this part, and I'm going to bracket this part so that I can square them nicely, okay? So I'm now imagining that this numerator is literally just like an a plus b squared, which we know would be a squared plus 2ab plus b squared. And it's important to note here that this x bar and this mu, they're not the same as each other, okay? This is the population mean, and this is the sample mean. So they're not necessarily the same as each other, which is why we can't just say, okay, let's just get rid of this. This whole thing is 0, because it has a distribution. So let's expand these brackets. Now, if I'm treating this as a, I'll get an a squared first of all. So my first thing is going to be from r equals 1 to n, I will have x minus x bar squared, and the denominator is obviously going to be a sigma squared. Now for the next part, I'm going to have two lots of, because it's 2ab, two lots of, from r equals 1 of n, of x minus x bar minus mu, all over sigma squared. So I'm doing that 2ab part. And then the last part is the b squared, which is going to be from r equals 1 to n of x bar minus mu, all squared, over sigma squared. Now, is there anything that we're interested in here? Yes. Ooh, I'm starting to see something that looks like it could be quite good. Okay, it looks like I am finding this thing that I've got here. That looks like it's basically the same as this thing, because these things in the sigmas, they could all say r equals 1 to n, technically. These have all got r equals 1 to n with them. So that's cool. That's the thing I'm looking for. I'm going to highlight that in yellow and see if I can deal with the rest of the other things that we have got. So let's see, which one do I want to deal with? I'm going to deal with this one in the middle, okay? I'm actually going to take out of this part, this is a constant and this is a constant. So for this one in the middle, I'm going to take out the 2, because obviously this is going to be a constant value that we've got here. X bar is just the sample mean and this is the population mean. So I'm going to have two lots of x bar minus mu over sigma squared, the sum from r equals 1 to n of x minus x bar. Now the sum from r equals 1, the sum of this thing that we've got here, I'm now going to investigate this. So this thing is the sum of x minus the sum of x bar. Well, this is just n lots of this constant, this x bar. So it's going to be minus n x bar. And the sum of x, if you think about where that comes from, we know that x bar is the sum of x over n. So the sum of x is just equal to, when you multiply it by n x bar. So this whole thing is therefore equal to 0. Which means this whole section in the middle can get completely removed because it is equal to 0. So I'm going to rewrite that line in purple with all of this crazy working. This is not how I would do things in a formal proof. This is how I want to explain it as best as I can do. So we've now got that the sum from r equals 1 to n of x minus x bar squared over sigma squared. The 0 bit is gone. We've now got the sum from r equals 1 to n of x bar minus mu squared over sigma squared that we have. Whew. Okay, I'm not going to adapt this thing. This is the thing I want to keep a hold of. I'm now going to think about what this actually means. Well, this whole part is a constant. This whole thing here is a constant. And we've got n of them from 1 to n. So I'm going to have n lots of this on the next line. This means I have from r equals 1 to n of x minus x bar all squared over sigma squared. And I therefore have n lots of x bar minus mu squared over sigma squared. It's literally just been multiplied by n because I've got n lots of the constant at that point. Now this is where you might be like, whoa, I would never have spotted that. And to be honest with you, I wouldn't have spotted that, this next thing, but it's true. So I keep highlighting it in yellow because I'm like, this is the thing I don't want to mess with. So I get this thing over here. Now this thing, believe it or not, is the same as this. It is x bar, let's do a bigger bracket for this. This is the same as x bar minus mu all over sigma over the square root of n all squared. And you're probably thinking, why am I doing that? I will show you why I'm doing that in just a second. Now let's just double check that this is the same thing, okay? If I was going to square the numerator, that's fine. I would get x bar minus mu squared. Now the denominator, if I squared it, would be sigma squared over n. I've got a fraction within a fraction, so if I multiply the top and bottom by n over n, then those bits would cancel, and I would have n x bar minus mu squared, n x bar minus mu squared, all over sigma squared. So this and this are equivalent from each other. We've basically forced the n inside, and we've also forced it into the denominator. Now, the reason I've done this is because this particular thing that we've got right here, which I'm going to show in purple, this looks like the standardized version of x bar. X bar has a normal distribution with a mean of mu and a variance of sigma squared over n. So if I was going to standardize this, I would standardize it as x minus mu divided by sigma over root n, and it's simply been squared. So it is a z squared. Oh, that's cool. It's a z squared. If it is a z squared, if it's a normal distribution that has been squared, we can say that it is a chi-squared distribution with degree order 1. So, keeping the thing in yellow that I want highlighted, I can now say that the second part of this, x minus x bar squared over sigma squared, this is a chi-squared distribution of order 1. And do you remember what we originally said that this thing here was? This thing here is a chi-squared distribution of order n. We said that here, right? It's a chi-squared distribution of order n. So this is a chi-squared distribution of order n. And I want to figure out what this thing right here is. Well, if this is a chi-squared distribution of order n, it is n lots of normal distributions being squared and added, and I've got one lot of a normal distribution being squared. So it makes sense that if I have this one take away this one, I've only got n minus 1 of them. So I can see here that this should be this thing that we wanted in yellow. Now, all that's left for me to do is to convince ourselves that the part in yellow is the same as the part at the top, and then we're nearly there. So is that true? Is this thing the thing that we had to begin with? Well, yeah, it is, right? Because the sigma squared can be at the bottom. Oh, I'm going to actually just change that for this final one, okay? I'm going to change it, and I'll put the sum in the numerator from r equals 1 to n, and I will put the sigma squared kind of across the whole thing, which is equal to n minus 1 s squared over sigma squared. Hence, what we have here is that n minus 1 s squared over sigma squared has got a chi-squared distribution with n minus 1 degrees of freedom. I mean, this is a bonkers proof, right? I would not be expecting anybody to kind of grasp all of this like right away, but I'm hoping that some of these things as we went about them made sense. So let's just quickly like re-summarize what it was that we did at the beginning. We said that we wanted to check that this had a chi-squared distribution, so we began by finding out what n minus 1 s squared over sigma squared was, and it turned out to be this yellow thing here that I wanted to find the distribution of. I knew that x and z were like this, and I knew that a chi-squared distribution was when we were adding up lots of normal distributions squared. And so I knew that I could restate this as, instead of summing up lots of z's squared, I could do the standardized x variable squared instead. So I investigated this by doing a little sneaky bit of rewriting the numerator with a minus x bar and a plus x bar, and I expanded the brackets. I found out that this gave me the thing I wanted originally up here. The middle part I found out to cancel because I knew that this part became 0 by looking at the stuff in blue, and I just needed to investigate this last part, which was actually just a constant being summed up n times, so it got multiplied by n. I did a sneaky thing here where I put the n back inside and it went into the denominator like this, which then looked like a x bar. It looks like the standardized, this looks like a standardized version of the x bar distribution, which told me that this was also a normal distribution being squared, which meant I could write it as that it had a chi-squared distribution with order 1. Then you had to trust me that if it had degree order n and degree order 1, I could say that this thing here must have had degree order n minus 1, which means that I could then say that this thing was distributed in this particular way. Now, if you didn't like the fact that I was saying a chi-squared was equal to something, I suppose I probably could have, in all of these places here, I could have, instead of writing this thing, I could have written that this was qn, and I could have written that this thing here, I could have said was q1, and I could have written that this thing was qn minus 1. So I suppose, really, if I was going to be doing it with that q language, I'm actually saying that n minus 1 s squared over sigma squared was equal to q n minus 1. And we know that q n minus 1 is distributed with a chi-squared distribution of n minus 1, which therefore means that this thing is true. Just because we don't normally write a distribution being equal to something, but I kind of feel like it wasn't that. It was fine for me to kind of do it in this way. So now we have that, hopefully you can believe me, that if we take the sample variance, we multiply it by 1 less than the size of the sample and divide it by the population variance, that would have a chi-squared distribution with the number of degrees of freedom of 1 less than the sample size. Okay, next video, we're going to start thinking about how we use this to come up with confidence intervals for variance, because all we've done so far in chapter 5 was confidence intervals for the mean. Well done for getting through a pretty crazy proof, and actually I think it was very, very interesting. So I'll see you in the next video.